this one over here isn't a quadratic. So in order to factorize it, we might have to use some of the techniques that we've learned in methods. And I noticed that this is z squared and this is z to the 4. So I reckon I can use some substitution here. So let's go z to the 4 plus 3z squared minus 28 equals 0. And I'm going to give that a go. I'm going to say let z squared equal k. So now what I've got is k squared plus 3k minus 28 equals 0. And 7 4s are 28, and 7 minus 4 is 3. That's going to work. And so I can have k and k, 7 and 4, plus 7 minus 4. And I can put my z squared back in there. You could have factorized straight from that. I can't do that easily. So then I'm going to rewrite it as z squared plus 7 and z squared minus 4 equals 0. Now, I want you to notice something. This z squared minus 4 is already a perfect square. Or a difference of perfect square. Okay, so that's z plus 2z minus 2. I can get that factorized. But z squared plus 7 is a bit of a problem child, unless you know about complex numbers, because I can just make it into a difference of perfect squares. So z squared minus 7i squared. I mean, why can't I do that? Of course I can. Z squared minus 4 equals 0. All right, now I've got two differences of perfect squares. So I've got z minus square root of 7i, z plus square root of 7i, z minus 2, z plus 2 equals 0. Okay, and now I've got a null factor law. They've asked us to solve it, so I now need to get it to the point where it says z equals. I've got z equals root 7i, or z equals negative root 7i, or z equals 2, or z equals negative 2.